So for the final subunit in the acids and bases unit, this is the last HL section, it's pH curves. By the end of the unit, you should know the characteristics of the pH curves produced by a combination of strong and weak acids and bases, a relationship around acid-base indicators and which one to use, the relationship between pH range of an indicator, which is a weak acid, and its pKa value, know what a buffer region is, the composition and action of a buffer solution, and the general shapes of the pH against volume for titrations of range of weak acids and strong acids and weak bases and strong acids. And the nature of the acid-base buffer may remain the same, but that buffer solutions can be prepared by either mixing a weak acid or base with a solution of a salt containing its conjugate. Also, you'll be able to select the appropriate indicator for a titration and predict the relative pH of an aqueous salt solution formed by the different combinations of strong and weak acids and bases. Let's get to it. So, the salts of weak acids and bases react with water in such a way that the pH of these salt solutions are not neutral. Okay, so for example, if you dissolve iron chloride in solution, or iron 2 chloride, then the iron 2 chloride ion will be hydrated and react with the water in an equilibrium, which will form iron hydroxide. Therefore, a salt of a weak base will make a solution slightly acidic. And therefore, you could also see that with a weak acid, a salt of a weak acid will make a solution slightly alkaline. So sodium ions will not convert to sodium hydroxide, chloride will not convert to HCl, as they are strong acids and bases. So basically the rule for this is that weak acids and bases are quite strong at holding on to their hydrogen or hydroxide ions. Another important component is buffers. Okay, buffers are also very important in biology. Okay, and a buffer is a solution which resists change in pH when small quantities of acids and alkalis are added. Okay, so it's a nice 2-mark question right there. Okay, so an acidic buffer has a pH less than 7. It's made from a weak acid and its sodium or potassium salt, for example, ethanoic acid and sodium ethanite. And an alkaline buffer, of course, is going to be greater than 7, and it's made from a weak base and its chloride, for example, ammonia and ammonium chloride. And they're used essentially in biology mostly to prepare buffering biological systems, for example, in the blood. Okay, so there is, of course, a buffer system working in your blood to maintain its pH around about 7, and also maintaining pH of shampoos, for example, or standardizing pH meters. So buffer solutions must consider ideal concentrations. Okay, the concentration of a buffer solution is critical. If the concentration is too low, there won't be enough of, say, the weak acid and the associated conjugate base to cope with the addition of extra ions. So for an acidic buffer, a solution needs, say, a large parent acid for dissociating into protons when alkali is added, okay, and large conjugate base to remove associated protons when they are added. This situation can't exist if only acid is present. A mixture of acid and salt is used. So the weak acid provides the equilibrium and the large weak acid solution concentration, and the sodium salt provides the large conjugate base concentration. So one uses a weak acid plus its sodium or potassium salt for this exact reason. Okay, so how do buffers work? Well, basically you've got two reactions working simultaneously. Okay, you've got the first is the equilibrium, where the weak acid is of course in equilibrium to form the associated conjugate base and protons, and the sodium salt form of the conjugated base goes completely into solution to the associated conjugate base plus a sodium ion. Okay. So if an acid is added, for example hydrochloric acid, it will completely dissociate to form protons and chloride ions, and these excess protons will cause equilibrium to be pushed to the left. Okay, so we're now looking at, of course, this equilibrium here. It will be pushed to the left, and so the pH remains the same. Okay, because you're basically creating more of the weak acid in solution. And if a base is added, for example sodium hydroxide, because of course that'll completely dissociate to form sodium ions and hydroxide ions, then the equilibrium will move to the right, because protons, these guys here, these protons will of course be taken out of the equilibrium, okay, because protons are going to react with the hydroxide ions to form water, and because the proton ions in the top equation are being taken out of the equation, okay, the equilibrium equation, then they're going to move, the equilibrium is going to move to the right to try and create more protons, so the pH again remains the same for that particular system. So note that state systems must also be written with these equations in the exam, even though I haven't done it on this particular slide. So you've also got to think about indicators. Okay, we've used them previously, and we've done titrations. So indicators are actually weak acids which have a different color to their conjugate base. Okay, so at low pH for this particular example, the equilibrium is pushed to the left. Okay, so at low pH for this particular indicator, you have the orange or red color. Okay, at high pH, the equilibrium is then pushed to the right, and you end up with this wonderful purple color for this particular indicator. Okay, because it's been deprotonated, and the deprotonated form as a purple color. Okay, so the example here is methyl orange. So at pHs less than 3.2, or the protonated form basically, so you notice this is protonated here. Okay, it's going to be a red color, and then as that proton is lost in more basic or alkaline solution, the proton's lost, and the color at pH is greater than 4.4 is going to be yellow. Okay, can you see that by this particular diagram? Methyl orange at the end point at around 4.4, it's going to be this kind of orange color. At an alkali, it's going to be yellow, and an acid is going to be this red color. Phenolphthalein, which you're probably more familiar with, at pHs less than 8.2. Okay, you're going to have the protonated form here, okay, which is colorless, and then the deprotonated form is going to, due to the change in absorption frequencies in the aromatic rings, it's going to be a nice pinkish color at pHs greater than 10. Okay, so in acidic conditions it's colorless, and in alkali conditions it again gets this nice pink color. So the relationship with the pH and pKa value of these two different indicators. Okay, so phenolphthalein has a pKa of around about 9.6. Okay, so the negative log base 10 of its acid dissociation constant is 9.6, whereas methyl orange is a lot lower, it's 3.7. The pH range it works in for phenolphthalein is 8.3 to 10, whereas methyl orange is 3.1 to 4. Okay, so they're going to be used for different acid-base reactions because of that. The color in the acid of phenolphthalein, an acid is colorless, whereas in methyl orange it is red. The color in alkali is pink, and it is yellow for methyl orange, and therefore phenolphthalein is very useful for titrations involving strong bases, whereas methyl orange is very useful for titrations involving strong acids, but due to the fact that the pKa's are so different and their ranges are so different. Okay. So those numbers may not necessarily make sense between pH and pKa, but they hopefully will now. Okay, so if you can see a standard indicator reaction here. Okay, so the protonated indicator in equilibrium with the conjugate base of the indicator plus a proton. Okay, you'll see different colors. Okay, for litmus it's red, the protonated form, and the deprotonated form is blue. You can therefore get a corresponding equation from the equilibrium law for the dissociation constant. So when the pH equals the pKa, the color will be midway. And if you increase the proton concentration at that point, it pushes the indicator to the acid color. It takes about 10 times difference in indicator color species to see the color change. Therefore, most color changes happen within about 2 pH units. Okay, so when doing titrations, if the indicator has to work, the pH of the range of the indicator's color just change within the range of the pH of the endpoint. Okay, so for methyl orange, the color at low pH in acidic conditions is red, and that pH change happens between 3.2 and 4.4, and the color in alkaline solution is orange, whereas phenolphthalein, it is colorless in acidic conditions. That pH range of the color change are higher in more the alkaline area of 8.2 to 10, where the color change comes to purple. This is why methyl orange is great for strong acid titrations and phenolphthalein is great for strong base titrations, because you consider where the color change occurs and what the pH range is. Okay, so in terms of pH curves, there are 4 different pH curves when you're doing titrations. Okay, so we'll look at the range of pH curves and then also consider what the best indicator to determine to be used in the titrations are. So the 4 types of titrations are strong acids, strong bases, which you're probably most familiar with, okay, because we've probably done hydrochloric acid and sodium hydroxide titrations previously. Okay, you've got weak acid and strong alkali titrations, which you're probably not familiar with because we haven't really done many weak acids yet. Strong acids and weak bases, which we haven't really done either, or weak acids and weak bases. Okay, so in the following examples in the next few slides, the alkali will have a concentration of 0.1 mole per decimeter cubed, and it is added to 25 centimeters cubed of the acid, which will also have a concentration of 0.1 decimeter or 0.1 moles per decimeter cubed. Okay, the endpoints themselves need not be neutral due to the phenomena of salt hydrolysis. Okay, so first, before we look at the titration curve, let's get some terminology out the way. Okay, so the first one is the equivalence point. Okay, and that's the exact point in which the solution is neutralized. Okay, for the given acid. And that's given as a volume. So that's when the concentration of the acid equals the concentration of the base. We also have the endpoint, and that's the point in which the indicator changes color, and it's given as a pH value. Okay, and that's related to the equivalence point. The point of inflection is the place in the pH curve where the largest changes in pH occur. Okay, and that's we're going to obviously where the steepest part of the graph is going to be, or the curve. Half equivalence is the point in the graph where half the acid has been neutralized and turned into a salt. And the buffer region is the point in the graph which is most resistant to changes in pH, which will be the areas of the graph where the gradient is least. Right, so the first one we're going to look at is a strong acid versus strong base. Okay, hydrochloric acid being titrated against sodium hydroxide. Okay, so we'll start right at the beginning where you have no alkali being added. Okay, so at the start, because there is no alkali yet, it's completely all hydrochloric acid. The pH is around about 1 because you only have 0.1 moles per decimeter cubed of hydrochloric acid. Okay, now what we do is slowly add the sodium hydroxide. Okay, and you'll see there is very little change. Okay, in this region here. okay, with the initial 20 centimeters cubed. Okay, so remember there's 25 centimeters cubed of the acid, and we're adding 25 centimeters cubed of the base. And then all of a sudden, at 25 centimeters cubed of the alkali being added, there's a very quick and sharp change in the pH over the addition of less than a half a drop of sodium hydroxide. Remember when you did this how hard it was to actually see that color change. It just kind of happened immediately. Okay, so that just then it jumps straight up into around about pH 13 and then or pH 12, and then it kind of slowly levels off as you add a little bit more sodium hydroxide, another 20 mils of sodium hydroxide, 20 centimeters cubed of sodium hydroxide, and it stays about the pH of 0.1 moles per centimeter cubed of sodium hydroxide, or it is a strong alkali. Okay, so that's a curve for a strong acid versus a strong base. And you can clearly see there's very little in the way of buffer regions, if any. Okay. And any of the indicators listed will be suitable. They all change in the vertical position. Okay, so you can use phenolphthalein, litmus, or methyl orange for the indicator of a strong acid and a strong alkali, because they're all within that range. So then we consider the strong acid against a weak base like ammonia. So just like in the strong acid, strong base, there is very little pH change during the initial 20 centimeters cubed of ammonia being added. Okay, and then again, then there's a sharp change in pH over the addition of less than half a drop of ammonia, just like we had in the previous example. But then notice the curve doesn't level off as quickly as that of a strong base, okay, because now you've got the formation of a salt, ammonium chloride. And the curve levels off at a pH of around about 10 due to an excess of 0.1 mole per centimeter cubed of ammonia. Okay, so it's not quite as high as pH 13 because it's a weak base. So it's kind of similar. Now, in this particular case, we can no longer use phenolphthalein, and we can no longer use litmus as acceptable indicators. Only methyl orange is going to be suitable because it's the only one to change in this vertical portion, okay, in the actual endpoint. Okay, so it's going to be in the range of around about pH 4. Okay. So litmus doesn't change during that range, and neither does phenolphthalein, so it's only methyl orange that can be used for titration of a strong acid and a weak base. Okay, so instead of starting at pH 1, it starts at a pH value of 4 because ethanoic acid is a weak monoprotic base. So 0.1 mole per centimeter cubed solution of that will be around at pH 4. And you'll notice now it's not a no change as you add more base. You're now getting a steady pH change. Okay, it's not flat-lined just like it would be for the last two examples. You're getting a steady increase in pH. And then as you've added 25 centimeters cubed, okay, at the equivalence point, there's again a sharp change in pH over the addition of less than half a drop of sodium hydroxide. But notice where the pH changes, it's about 6.57, okay? And then the curve levels off at pH 13 very sharply due to an excess of 0.1 mole per centimeter cubed of sodium hydroxide, the strong alkali. Okay, so it goes from 4 to around about 13, but you'll notice this section of the graph here, due to the formation of buffers, is a steady pH change rather than just a quick leveling off. And for this example here, only phenolphthalein this time is suitable, It's the only one to change in the vertical position, okay, at that kind of point of inflection, that end point. Okay, both in litmus and methyl orange's case, it's not going to actually change color within that particular range. And then we have the weak acid, weak base. Again, it starts at pH 4 due to the pH of 0.1 mole per meter cubed of ethanoic acid. Again, you see the steady pH change. And you'll also notice this is the first example of no sharp change in pH when you've added an equal amount of the weak base. And you've also got a very gentle curving of the leveling off, this time to pH 10, which is the pH of the weak base, due to the excess of this weak base. Okay, so it's a very gentle inflection point rather than a sharp one, which we've seen in the previous examples. And this particular case, there is actually no suitable indicator. None change actually at this point of inflection in terms of the vertical portion. The endpoint can be detected by plotting a curve only using a pH meter, so you cannot use indicators for a weak acid, weak base titration. So in summary, the choice of indicator for an acid-base titration depends on the relative strengths of the acid and base, and therefore on the pH of the equivalence point. Okay, so remembering, of course, the equivalence point is where the concentration of the amount of moles of the base equals the number of moles of the acid. Okay. The midpoint of an indicator's color change must correspond to the equivalence point of the titration. Okay, and the equivalence point is basically this vertical line here. Right. The titration of a strong acid and a strong base, such as hydrochloric acid and sodium hydroxide, which we've gone through, has an equivalence point of around about pH 7. Which means that it falls within the range of phenolphthalein. Okay, so you can see for strong acid, strong base, then that does fall within the equivalence point of the strong acid, strong base. Okay. The rise covers the pH range of the most acid-base indicators. So all common indicators, just as such as phenolphthalein or methyl orange, can be used for such titrations of strong acids and strong bases. Okay, whereas the titration of hydrochloric acid with the weak base ammonia has an equivalent point which is going to be less than 7. And only methyl orange is going to fit within that. Okay, so you'll notice the equivalence point of a strong acid, weak base is in this area here, which doesn't fit within the color range of, or color change of phenolphthalein, so you can't use phenolphthalein for that. Okay, and the titration of a weak acid and a strong base, okay, so we're looking at here again, okay, as a pH equivalence point which is greater than 7, okay, and because phenolphthalein has a pKa of 9.6, it is again effective for this titration because there is the color change there. Okay, that's for phenolphthalein. So if you look at methyl orange, again, methyl orange is effective for a strong acid, strong base. Okay, because the color change happens here. Okay, that's fine. Okay, it falls within this area here. For a weak acid, weak base, it's useless, okay, because the color change doesn't fall within that. And for a strong acid, weak base, okay, again, you can use methyl orange for that because the color change of the indicator falls within the range of that equivalence point.